Hi everyone, today we're going to be learning about applications of integrals, specifically in biology when calculating cardiac output. This lesson is equivalent to section 8.4 in the James Stewart Single Variable Calculus Early Transcendentals 7th edition textbook. I'll be going into detail about cardiac output, its significance in the body, and how integrals can be used to calculate it. Then, we'll look at some example questions to solidify the knowledge. Let's begin. Firstly, what is cardiac output? It obviously has to do with the heart, but what does it really represent? Well, cardiac output is essentially the volume of blood expelled from the heart to the aorta over a certain amount of time, and it's usually measured in liters per minute. Here's a diagram of blood flow in the heart, from the right atrium to the right ventricle to the lungs, then back to the heart, into the left atrium, left ventricle, and finally the aorta, to be transported to the rest of the body. The simple equation for cardiac output is Q, or cardiac output, is equal to stroke volume times heart rate, which is essentially the volume of blood expelled per heartbeat divided by heartbeats per minute, ending up as volume per minute. Monitoring cardiac output is extremely important as it can indicate abnormal heart rate, stroke volume, or cardiac muscle strength. Now that we've learned some of the background information about cardiac output, let's get into how we can actually solve for it. Though there are many effective methods, the one related to integrals is the dye dilution method. The dye dilution method uses dye that flows from the right atrium to other chambers of the heart and eventually to the aorta. A probe in the aorta measures the concentration of dye at equally timed intervals until the dye has cleared completely. Now let's see how we can use this to determine cardiac output. Let's let C of t be the dye concentration, delta t be the time interval, A be the amount of dye, and Q be the cardiac output. We know that A equals C of t times Q times delta t because of this explanation. Though this equation is effective, it only gives us the amount of dye per time interval. We, however, want the sum of the amounts of dye. Thus, we will use sums, where the total amount of dye is the sum of the concentration times the cardiac output times the time interval. Since we want the most accurate sum, we assume that the number of time intervals approaches infinity. Then, we can convert the sum equation into an integral equation. If you require extra help with this, you can review the definition of a definite integral on page 372 in the textbook. After we've converted the sum to the integral, we get the equation, the total amount of dye is equal to the cardiac output times the integral of the concentration. We can change this equation so that we can isolate the cardiac output, and we get that cardiac output is equal to the amount of dye over the integral of dye concentration. Now that we've derived the formula for cardiac output, let's put it to use in some examples. In the textbook, you will see two types of cardiac output questions, ones with the dye concentration equation and ones with the dye concentration table of values. Let's do an example of each. Example 1. The dye dilution method is used to measure cardiac output using 10 milligrams of dye. The dye concentration in milligrams per liter is modeled by Ct equals 2t e to the 5t squared, over the time interval 0 to 10 measured in seconds. Find the cardiac output. The first thing we do is set up the integral for dye concentration. It is a definite integral where t, or time, belongs to the interval 0 to 10. We can bring the 2 outside the integral and then solve the integral. To finish solving the integral, we use the theorem of calculus. We end up with e to the 500 minus 1 over 5. We can then plug it into the cardiac output equation, where Q is the amount of dye divided by the integral of the concentration of the dye. Thus, we divide 10 milligrams by e to the 500 minus 1 over 5. Eventually, we end up with 50 over e to the 500 minus 1 liters per second, which can be converted to liters per minute by multiplying by 60. The next example we will cover involves a table of values. When presented with dye concentrations in table form, one must use Simpson's rule to estimate the integral of the concentration. Simpson's rule is useful in estimating integrals using parabolas instead of straight lines. The equation of Simpson's rule states that the definite integral of an equation is the time interval divided by 3, or delta t over 3, multiplied by fx null plus 4 times fx1 plus 2 times fx2, with all other function values multiplied by alternating 4 and 2, with the final function value, or fxn, being multiplied by 1. Remember, Simpson's rule can only be used with an even number of subintervals. And now for the example. 7 milligrams of dye is injected into the right atrium. The concentration is shown using a table of values where delta t is 1 and t is measured in seconds. Estimate the cardiac output. First, let's find the integral of the concentration from 0 to 6. We will use Simpson's rule like so. Then we will divide the amount of dye by the estimated dye concentration, which gives us 7 over 14, or 1 over 2 liters per second, multiplied by 60, that is 30 liters per minute. That's all for today's lesson. If you wish to review any concepts covered today, you can find them on pages 372, 513, and 565 in the James Stewart 7th edition Single Variable Calculus Early Transcendentals textbook. Thank you for watching and have a great day.